All right, here we go. Chapter 21. This is all about stellar explosions. So this is the star at the very end of its life, um, and we'll talk about the different types of stars that can do this. Just as a note, Chapter 22 and Chapter 21 are very much related. Chapter 22 is really black holes and neutron stars. It's really the result of these stellar explosions, or one of the byproducts of the stellar explosion, possibly, as we'll see in Chapter 22. Like I said, I've used many different textbooks over the years, and a lot of them combine these, and they don't have them as separate chapters. So it's fine that they have two different chapters. But all right, so they're very much related to each other. All right, so these are the things we're going to cover. So what happens to some white dwarfs, depending on whether they have a companion or not, of one of these high mass stars, and of course supernova. Right. This is really what this chapter is about. Is the supernova. There's actually two different types of supernova. Well, two main types of supernova. There's the last really major supernova that occurred near us, and I use quotes around that near because it was actually in another galaxy, a galaxy not too far from the Milky Way, but it was technically in another galaxy. Anyhow, the formation of elements. This is also known as nucleosynthesis. How did the elements get here, get onto our planet, and other planets as well. And then the cycle. It turns out that stars are wonderful at recycling. They recycle themselves, as a matter of fact, as we're going to see. All right, so let's get into this. One of the things that we find is, let's say you had a white dwarf, and this is, as we talked about in Chapter 20. This is the end of a low mass star. There have been times, and these have been reported even historically, where all of a sudden this very dim object becomes extremely bright, and you can notice the luminosity in some cases can go up 10,000 times, and then it'll take maybe 100 or maybe 100. This particular one takes 100 to 150 days for the light to start dimming again to back where it was. All right. So what happened? We thought that before we were talking about white dwarfs as being dead stars, and of course it's because these particular white dwarfs, which again, I've said this many times now. If you look in the galaxy, in our galaxy, and you take a survey, most of the stars, a little more than half the stars have a companion. Right? Our star does not, of course. We just have the sun. Jupiter is way too doesn't have enough mass to even approach becoming a sun. It would have to be about 80 times more massive than it currently is to ever even think about becoming a star. So anyhow, most stars are like this, and so here's what can happen. You have this white dwarf, all right. So and the other star is close enough that that there can be material that can pass through the Lagrange point and accumulate in a manner that we call accretion. All right, accretion is just in fact, we're going to talk a lot about that when we get to black holes. So accretion is when matter basically accumulates at or near the surface of the star. And one of the things that we're going to find is when during this accretion process, and it's called, as it says here, an accretion disk, that material will actually basically rub against itself and heat up, and it heats up enormously, as we're going to see, and so the material is falling onto the white dwarf, and is the white dwarf is accumulating more and more mass. So what can happen and this is the bright, that's what this object is. Okay, this is an actual, what they call a nova, which the star gets very, very bright. Right. So what's going on is, again, you have a binary, you have a companion that is basically donating part of itself to the white dwarf. The material accumulates, and then the white dwarf gets hot enough that nuclear fusion takes place. Hydrogen, right? Hydrogen is turned into helium, right? And that it causes this enormous flash. It's not as intense as a supernova. There's definitely a big difference between them. The other thing to notice about this, and we've actually witnessed this, that some of these, it depends on how much mass the companion has. Some of these will repeat, and you'll have these semi-periodic nova. All right, so it's not anything you can sit there and time. You can't use it like a clock or something like that. But they do. There have been situations where they do repeat. And so now we see here's the star, and there is, after this giant thermonuclear explosion on the surface of the white dwarf, material comes flying off. Right, very similar, of course, to although it's different, but similar to the planetary nebula phenomena. Right, of course, the planetary nebula phenomena is the original mass of the star moving outward due to expansion of the star. Anyhow, this is material that is accumulated on the surface of the star, and some material from underneath the surface of the star starts to expand out into space after a nova. Okay, so nova just means new in Latin, and so there was basically, you go back into the Middle Ages. There are reports of people seeing a star where there had never been a star before. Of course, the stars were there, or the star that they observed was certainly there before that. It's just that it became bright enough to see with the unaided eye, which, of course, that's all you could do in the Middle Ages, naked eye observations. All right, so now that's different than a high mass star. Okay, so with a high mass star, so we're talking about 8 or more times the mass of the sun. What happens is the fusion continues, and you'll build kind of like an onion, where you get heavier and heavier shells of material until you get to the core, which will eventually become iron. And there'll be an iron core. And when the iron begins to, when the star reaches to the point where it can fuse element 26, which is of course iron, it's ready to die. It's ready to explode, basically, and it takes a very short amount of time for the star to collapse in on itself. Now, why iron, you might say, and this really shows it. If we do a plot of mass versus the number of nuclei, we see that iron turns out to be the most stable element there is. So, for example, you can have fusion that creates heavier and heavier elements, and until you reach iron, and then we'll get to how this happens. But let's say there are heavier elements like uranium and other things, lead and so forth. When these things break down, if they do, that not all forms of lead break down in radioactive decay, but if there is radioactive decay, they would head towards iron. Right? Okay, so this is in stars. So keep that in mind. This is inside of like a massive star. So, that's why we're talking about iron. All right. Now, what happens is, remember, you always have the inward pressure due to gravitation, right? And for a massive star, that's a lot of pressure. Basically, nothing is able to stop the star from, once it starts to create iron, there's nothing that will stop it from imploding, right? It ultimately will explode, but the core crashes in on itself in like a second or so. And what happens is, we kind of talked about this before, but now this is actually we didn't talk about specifically this, but the same kind of thing. In this particular case, what's going to happen is, as the core crashes in on itself, protons and electrons, which are floating about in this this very, very heavy star, will actually undergo a nuclear reaction, and we can actually do this in our laboratories, where the protons and electrons will form will actually form neutrinos and also neutrons. Okay, so neutrons are the most important. And so this is the main thing, is you're creating neutrons, and actually tons and tons of neutrinos as well. Neutrinos, by the way, are these tiny particles. We talked about these in chapter 16 with the sun. These are these tiny particles that almost have no mass and travel really close to the speed of light. If we were even aware of neutrinos, there are literally trillions of them passing through you like you're not even there right now. They're passing right through the planet, and they don't really interact very much with matter. But neutrons certainly do. Right? That's one of the main things that's in the nucleus. All right, so this is the end of the high mass star, the life of it. Neutrinos will escape, and what happens is the neutrons, right? So they're looking at this reaction right here. The protons and electrons join together in a process. I think it's called reverse beta decay. Anyhow, that doesn't really matter. You're creating neutrons and neutrinos, and the neutrinos leave, like I said, almost at the speed of light. They pass right through this, this exploding star, and escape into space. But the neutrons that are left behind will compress, and they will actually will remember that a star is always in this balancing act between the inward force of gravity and the outward push. Well, what's pushing? And so it turns out that some stars can stop the pushing, push the inward collapse, just because the neutrons will actually become degenerate, right? That is neutron degeneracy pressure. Just like there was this electron degeneracy pressure, there's this neutron degeneracy pressure that will push back, and that will happen after the supernova explosion, right? Because you have to have this supernova explosion to get all this stuff happening. And during the supernova explosion, that's when the heaviest elements are created, right? The very last rows of the periodic table. Here are the two types of supernova. Type 1 is shown in green right here. Type 2 has this this characteristic plateau, So the type 1, as we're going to find out, is basically a carbon explosion. We'll talk about that a little bit more. And then this is the white dwarf. All right, so here let's take a look at it. Sorry, not the white dwarf. Sorry, we'd already that's the nova. All right, so these are the supernova. Okay, so supernova will remember before we talked about nova, where the